This video completes the derivation of FEA using the principle of stationary potential energy. Please make sure you watch video energy methods 1 before you come into this one, because we're going to pick up right in the middle. In the last video I showed you how you can take the principle of stationary potential energy and combine that with variational calculus in order to come up with an expression that certainly resembles the system of equations that we need for finite element analysis. In order to apply that technique, though, first we have to be able to express the total potential energy in terms of the unknowns in our problem, the nodal degrees of freedom, or specifically the nodal displacements. So, returning to the idea that total potential energy is made up of two main pieces, internal strain energy and the potential of forces to do work. Let's look at each of those and see if we can define them in terms of the nodal displacements. So, first off, the internal strain energy. We can express this as the product of the stress vector and the strain vector, integrate that over the volume and put a 1/2 out front. So this is a general expression for the internal strain energy of a body that is subjected to stress and strain. We can look now at the stress vector. I'm going to elaborate a bit on what we've previously talked about in these videos. The basic idea of stress is equal to the D matrix multiplied by the strain is generally true, but not true for certain cases where we have thermal strains present in the problem or when we have initial stresses. If we want to consider those two cases as well, we have a more generalized expression as shown here. So the thermal strains have to get subtracted off from the total strains that we have, including the loaded strains, and then the initial stresses need to be added on in order to have a complete expression for the strain present. So if I look at the transpose of the stress vector in order to put it into this integral, when you take the transpose of a product of matrices, you have to reverse the order, and you can confirm for yourself this is the case in terms of the product rules with the matrices. So I get this expanded expression for the transpose of the stress. Now what I'm going to do is plug that into my expression for the internal strain energy. So I get the first term, including the strains from the loads. This is the only term that would be present if I'd have no thermal strains or initial stresses. But if I have those, I get a thermal strain term that has an epsilon 0 in it, and I have an initial stress term with a sigma 0 in it. So this is a general expression for the internal strain energy expressed in terms of strain vector and residual stresses. Now let's look at the omega term, or the potential of forces to do work. Recall that the potential of a force to do work is just the negative of the work that would be done if positive displacement occurred. And displacement is u, that's my displacement vector. So if I take the product of displacement and force, that will give me work integrated over the volume. So the negative of that gives me the potential to do work. What I'm going to do is break the forces into 3 different components. So the first one I've got showing here is the body forces. So I've got my expression for the displacement field multiplied by my body force vector, and then I integrate that over the volume. I also want to consider forces that might be acting on the surface of my body, or surface tractions. So similarly, I'm going to have the displacements at the surface, the displacement field on the surface, multiplied by the surface traction. So the distinction between these two terms are integrating over the volume, integrating over the surface, and also that body forces are force per unit volume and surface tractions are force per unit area. Then I have a last term I will add in because you might want to include point loads in your system. Now in FEA, those point loads will be acting at nodes. So rather than looking at a displacement field, I simply look at all of the displacements at all of the nodes, or we also call that my degree of freedom vector, D. So that gives me the 3 components of potential to do work. So let's put that all together. Okay, so if I put all these together, I'm going to have the total potential energy, pi p, is equal to 3 terms that are integrating over the volume and that focused on the strain in the system. And then I'm going to have 3 terms that integrate 2 of them, well, 1 over the volume, 1 over the surface, and then the last one is simply the product of all of the nodal displacements that have forces acting on them. So a total of 6 contributions for potential energy. What I want to do is express each of these in terms of nodal degrees of freedom so that I can apply the technique we saw earlier and get a system of equations involving the degrees of freedom. So let's go back and recall the strain displacement and shape function relationships. The shape function relationship says that I can define my distributed displacement field U in terms of my nodal degrees of freedom through a matrix called N, the shape function matrix. And the strain displacement relationship says that my strain is given to me by some differentiation of my displacements. If I put those together, strain is equal to this partial derivative matrix operator acting on my shape function matrix. If I take those two pieces and multiply them by each other, or have the partial derivative operator act on the shape function matrix, I get a new matrix called B, or labeled B. I'm going to call that the strain degree of freedom matrix. So now I can say that the strain vector is equal to the B matrix multiplied by the degrees of freedom. So then I put this into my expression at the top of the screen there, and that gives me a new expression for the total potential energy in terms of the degrees of freedom. Let's walk through each piece of that. First off, I'm using the relationship between the strain and displacement to convert each of my strain terms from above into the product of the B matrix times the degree of freedom vector. Then next, I take each of my displacement the U expression, so the displacement field terms, and I'm converting that into the shape function matrix multiplied by the degree of freedom vector. So now that I have this expression that depends on the nodal degrees of freedom, I'm going to make the observation that the degrees of freedom are just a whole set of numbers. They are specific displacements at nodes, so they don't depend on position. Each term in that degree of freedom vector is associated with a different position. So I can remove the degree of freedom vector from within the integrals. So I do that, and now I see I have a whole bunch of degree of freedom vectors multiplied by other expressions. This allows me to then get into my little bit of my hand waving from before. So the equilibrium condition states that the variation of pi p equal to 0 is equivalent to stating that the derivative of pi p with respect to the degree of freedom vector is equal to a 0 vector. And recall that what that means is I successively take the derivative of pi p with respect to each one of the degrees of freedom. But in fact, if I use my bit of hand waving here, I take the derivative with respect to the vector d, which means I'm going to be canceling d terms. So you can see the pi p goes to, that's 0 now, that's the right hand side of the equation shown right here, the d pi p dd. And then this first term was basically 1/2 d squared times some quantity that did not depend on d, so it's just a coefficient. So the derivative of that is just going to be d times that coefficient. The second term is the term d, the vector degree of freedom, multiplied by some new coefficient. The derivative of that with respect to d is just the coefficient, and so on. So that gives me each of these terms. Now, this is a vector expression at the bottom of the screen here, as opposed to a scalar expression up at the top. This vector equation, or this matrix equation at the bottom, is my system of equations that I need for FEA. So I've rearranged terms a bit here. I've moved the one term that's still multiplied by degree of freedom over to the left side and everything else onto the right side. But all the same terms we just saw. But now this allows me to rewrite this as k times d equals f, where I've defined k to be this integral shown, integral over the volume of b transpose db dv. And then I have an expression for what I can now call my force vector, and it's made up of 5 pieces. The first 2 pieces listed here come from the body force and the surface tractions. The third piece is my point loads, and the fourth and fifth come from thermal strains and residual stresses, respectively. So let's assume that we don't have any thermal strains or initial stresses. We can add them in later if we want to deal with that. For right now, we'll just neglect them so we can see the force is made up of three terms: the body forces, surface tractions, and nodal loads. This gives us two fundamental formulas that we're going to use throughout all the rest of these videos to define stiffness matrix and force vectors for any type of element. This is a very powerful result that we have here. So this video has come up with a lot of equations, a lot of meat to this one. Let's do a quick summary of where we're at before I apply what we've done to the bar element. So first off, we have some strain displacement relationships, where we say that epsilon is equal to the partial derivative matrix operator acting on the displacement field. Secondly, we have stress-strain relationships. The simple form of that is just that the stress vector is equal to the constitutive law matrix D multiplied by the strain vector, but we also have a more complicated expression if we happen to have any thermal strains or residual stresses present. Then we have the shape function relationship. This defines the displacement field in terms of the nodal degrees of freedom using the shape function matrix. We also have a strain degree of freedom relationship. This is the definition of a new matrix B, which is the partial derivative matrix operator acting on the shape function matrix. So in other words, B is what relates the strains to the nodal degrees of freedom. And then lastly, we have the expressions we just derived based on stationary potential energy. So these are true for any system in equilibrium. We can say that we have a force vector equal to a stiffness matrix times a degree of freedom vector, where the stiffness matrix is given as shown, and the force vector has three components based on body forces, surface tractions, and point loads. So that's a quick summary of the equations that we've derived. Let's do a quick review for the 1D bar element, looking at its equilibrium derivation. So we had two equilibrium equations looking at two halves of the bar elements. Then we applied stress-strain relationships and strain displacement relationships in order to rewrite the equilibrium equations. And then lastly, we used the displacement field assumption, which is where our shape functions came in. Putting all of those together allowed us to convert the two equilibrium equations into a system of equations that look at forces and nodal displacements. And then that gave us a stiffness matrix, AE over L times 1, negative 1, negative 1, 1. Let's see what happens when we apply the energy principle to the bar element. See if we end up in the same place. So first off, we're going to make the same assumption about the shape functions. So shape function matrix is just 1 minus x over L and x over L. We're going to now have to derive a B matrix because we need the B matrix to get the stiffness matrix. So B is the partial derivative matrix operator acting on N. For the case of the bar element, the partial derivative matrix operator is simply d by dx. And N is as shown here in this first set of equations, 1 minus x over L and x over L. So that gives us a B that's just minus 1 over L and 1 over L. Note that this is constant. It does not depend on position. This means that our bar element is going to have constant strain in it, because remember the B matrix gives us the relationship between the nodal degrees of freedom and the strain inside the element. Okay, so now in 1D, remember that the D matrix is just Young's modulus E. So K is then the integral over the volume of B transpose times D times B. And we convert that into a integral over the length, where dV has become A times dx, and the B transpose and B matrices are added in here. Now it's simply a matter of pulling out the A and the E and multiplying these two matrices by each other. So we get the expression shown. We evaluate the integral, very simple now. So it's just going to give us an L, which will cancel one of the L's at the bottom, and we get that K is equal to AE over L times 1, negative 1, negative 1, 1. Exactly the same thing that we had from equilibrium. So the energy method works in this particular case, and we will see that it works rigorously on all of the other element types as well.